Okay, thank you very much. Good afternoon. This is a joint work with Renzo Ricca, probably you know him. And it is about twist effects in quantum vortices in Bose-Einstein condensates. So I will briefly review some concepts on Bose-Einstein condensates. I think all know about these concepts. Bose-Einstein condensate is diluted gas of bosons that's in temperature T equals 0 are all in the same ground state described by the wave function psi. And time evolution of such a condensate is well described by the Gross-Pitaevskii equation, which is a nonlinear Schrödinger equation. And for our work, we consider Bose-Einstein condensate fulfilling the entire space, R3, and the wave function goes to unity when we go far away. Of course, we have vortices with quantized circulation. Vortices are in Bose-Einstein condensates are zeros of the order parameter. So they are places where the phase is multivalued. And for us, multivaluedness means that there on the vortex, the phase can assume all the possible values. For our work, we use Madelung transformation. So as you already know, Madelung transformation permits you to watch the Bose-Einstein condensates as a quantum fluid with density rho and velocity v. Renz called u this morning, the velocity, I call it v, which is the gradient of the phase chi, which can be multivalued in presence of vortices. And obviously the hydrodynamics equations. But now the focus on twist. Twist is well defined for classical vorticity theory, but here we are talking about quantum vortices. So they are very thin singular lines, and so it is difficult, it is hard to generalize twist concept in Bose-Einstein condensate. So we use the concept of a twist phase, defined for the first time by Salman and then used by Zucker and Ricca in 2017. And what is a twist phase? Twist phase is a theta twist, is a perturbation of the phase of the condensate. In particular, if to fix ideas, we can fix an isophase surface, the simplest one. For simplicity, the disk bounded by the vortex, the blue one. And what happens? So the perturbation, theta twist, is a perturbing phase such that the entire perturbed phase, chi, is equal to the unperturbed theta plus theta twist. And such that close to the vortex, we have the classical twisting. So we have that the isophase, any isophase must turn around the vortex going along it. So it is produced a gradient of phase chi given by the gradient of theta twist along the vortex. So the physical effect given by theta twist, given by the twist phase, is longitudinal velocity along the vortex that we called v twist velocity. But in a previous paper, 2020, we tried to study, to twist a quantum vortex, a quantum defect, and to study its dynamics, what happens at a twisted vortex in a Bose-Einstein condensate. And what we found out is that the energy, a twist, is complex. The Hamiltonian that leads the dynamics is non-Hermitian. That means that we have gain and loss, some sort of gain and loss processes, and we have an unstable state in region where the Laplacian is greater than 0. So we discovered this by performing a linear stability analysis. And so what happens? There are Kelvin waves, sort of perturbation, and these Kelvin waves in this region are unstable, so their amplitude grows in time. But this C1, psi1 is the twisted states of the vortex. Okay, so we have an unstable state evolving like a non-equilibrium state, but obviously the total energy of the Gross-Pitaevskii equation must be conserved, must be real in some sense. So in a very recent paper, we tried to find out some stabilization mechanism in order to restore the reality of the energy. What happens to such an unstable state? Well, it depends. We discovered that it depends on the nature of the twist injected on the system. So you have to imagine to inject from outside a scalar function, theta twist, a field. For example, you can do this maybe by using Gauss-Laguerre beams on the system. And if we discover that we have totally different behavior if the injected twist phase is globally injected or only localized injected close to the vortex. What does it mean? Well, first, the global twist phase. A global twist phase can be defined like this. Is said to be global if it is present uniformly everywhere in the condensate. So to fix idea, it is present uniformly at all isophase surfaces, such that the twist velocity is parallelly transported along the natural frame. Natural frame is, if we fix the disk isophase surface, it is the green vector here, n, which is defined to be everywhere orthogonal to the vortex line and staying on the isophase surface. So the twist velocity is parallelly transported along this n if the twist is global. Here you can see an example of a global twist defined on the disk. It is discontinuous. It means that it is multi-valued. And if it is global, it is multi-valued as all the phase. And what happens to the isophase? The isophase, by injecting this global twist, is twisted like this one, and you can see the production of twist velocity. So in this case, we have a multi-valued twist, and so we can fix a cut surface, the green one, we call it sigma, and by using, again, Kleinert's theory that Renzo told us this morning, by using Kleinert theory, we discovered we could demonstrate mathematically that a secondary vortex will form at the center of the vortex. So why this happens? Because being multi-valued, there will be a region here where the phase theta twist can assume all the possible values. And so the twist velocity by Kleinert theory, which is the gradient of theta twist, has a non-zero curl omega twist that defines the purple line, vortex line. And this purple vortex line is exactly the boundary of this green cut surface. So since you will see in the next days, in a Bose-Einstein condensate, the helicity is identically 0. So in this case, an injected twist, the injected twist is balanced not by the writhe, but by a changing in linking number, if the twist is global. What happens now if instead of a global twist, we inject a localized twist? This is a very new concept we defined in recent paper. What is a localized twist phase? A twist phase is said to be localized on the vortex line L if it is confined to the tubular neighborhood T. So if the twisting effect on the isophase, for example, on the disk isophase, is confined only in a tubular neighborhood, and outside is 0. So in this case, we give an answer. We define the theta twist as a function, as a product of two functions, a function of the radial distance of from the vortex r, the radial distance from the vortex, and times a function g of s, which is the function of the arc length parameter. So it can change radially, and radially is a bump function. Sorry, is a bump function. So it decreases very rapidly to 0 at the center of the vortex and outside the tubular neighborhood. And while along the vortex, you can fix whatever you want. For example, here you have an example of a continuous sinusoidal vortex ring along the, theta twist along the vortex ring. Psi is the radius of the tubular neighborhood, which is the healing length. So we choose as the radial thickness, the healing length. So you have a twisted isophase only in a tubular neighborhood, and the twisting intensity, let's say, diminishes with increasing distance r from the vortex. Here you can see two ribbon models. By increasing r, you have twisting. I don't know if you can see them, but the twist of these two ribbons is decreasing with increasing r. So what happens in this case? In this case, this is the main theorem of our new paper. So let L denote a closed space curve that is a nodal line of a quantum defect in isolation. The defect is subject to a twist phase, theta twist. So we inject, for example, by a Gauss-Laguerre beam, a twist phase on all the condensate. And in particular, we can fix ideas thinking of just one isophase. And then, so we have at the beginning twist different from 0 and writhe equal to 0, for example, the vortex ring. And suppose you have regions where the Laplacian of theta twist is greater than 0. Remember, the energy is complex, and the stabilizing mechanism, the destabilization is due to the positivity of the Laplacian. Under this consideration and under conservation of zero helicity, we have in this case that the stabilization mechanism coils the filament. So if in this case a stabilization mechanism occurs, so some energy is lost from from the vortex string and acquired to produce the secondary vortex, stabilizing the system. In this case, the stabilization occurs when the filament is coiled. I just give you the sketch of a proof because it's a little bit boring. So first of all, we have instability. So instability is destabilizes the spatial the vortex, so its spatial configuration by Kelvin wave productions. Of course, there must be some redistribution of gain and loss. So energy must be real and must be conserved. And so there must be regions that compensate the positivity of the Laplacian. Then, of course, the energy, the E twist we defined at the beginning, must be minimized. So the gradient of theta twist must go to 0. And so this means that the defect tends to stay on an isotwist locus, but an isotwist locus is nothing but the twisted disk, the twisted isophase surface. So the vortex tends to stay on an isotwist, an isophase twisted surface. And this produces coil. Why? Because, and this is the main part of the theorem, during the destabilization, the filament tends to rotate, and also within it, also the tangent T. And we demonstrated by using the definition of writhe given by Binish and Alexander, 2018. They define writhe as the solid angle of the tangent indicatrix. Starting from this point, we demonstrated that the total angle of rotation of the tangent during this destabilization mechanism around a fixed direction Z is exactly right. So in this case, we have writhe production. So now, in this case, since helicity must be 0, there is no production of linking number. There is production of writhe that compensates twist. Because, you know, helicity is given by 3 quantities: linking number, twist, and writhe. But we don't know a priori what kind of character